Let's start today session on classical machine learning. Today, we're going to talk about classification algorithms. Let me start sharing my screen on a different topic. So this is the starting page for our data lab workshops that you are already familiar. And here you will find today's workshop. We're doing the classical machine learning. And if you go there, I'm gonna post a link in a while. So today we're talking about classification, and these are going to be the materials for today. So I'm gonna share it in the chat for you. Yes. Yes, let me reshare again. Okay. Okay, share everything. Okay, now you should be seeing the wiki. Yes, please let me know. Okay, so I have shared in the Slack, in the chat, the link for today's note. And so last week we talked about supervised machine learning regression algorithms. And remember that regression is when you build a model, and based in that model, then you can look for points that are not included, and the value of that new point is going to be returned by the model. Today, we're going to be looking at classification, and so I'm going to share the notebook. There are many algorithms there for specific classification. We have the logistic regression. Let me see. Sorry. Classification, yes. So this is the notes for today. So there are many algorithms there for doing classification, and I'm going to share a notebook. So in doing classification, we need to train our models. So we will have some initial data, and then after the data is already ready for the model, then we will split the data into two parts, the train and testing, to train the model and test the model. And then basically is this figure over here. So we have our data and we have to split our data. Usually it's this training data is, if you have plenty of data, it's about 80% of your data, and then you leave 20% for testing your model. And then once you train your model, then you test it, and then you have to have a list of metrics to see what is the performance of your model. So that's the idea. I'm going to go all the way down, and I'm going to share this notebook. So hope. And we're going to follow the discussion from that notebook. I'm going to post it in the chat again. And then the notebook for today is as follows. Then this notebook will open in a GitHub, and then you can select the notebook and run it in your Google Colab account. You're using your Gmail account. So we're going to do that and follow the discussion. And again, please let me know if I'm talking too fast, or if you have any questions, or you want to stop me and ask something that is not clear. All right, so we're going to do the classification using the Palmer's penguins data set, and that data set is one of the known data sets. It contains It contains data from 3 types of species of penguins that live on 3 different islands in the Antarctica. So, so we're going to work with that today. I'm going to open this notebook in Colab, so I'll be running it. So now I'm in Google Colab. This is the executable notebook. And we're going to be using, again, scikit-learn. We will be using scikit-learn library for all the classical machine learning tasks that we're going to be doing. And so the first cell, code cell, is always contains all the libraries we'll be using. So we are going to import the basic libraries NumPy and have the alias MP, pandas and alias PD, and stats model API as SM. And then we will have to visualize some of our data. So we're going to use matplotlib, pyplot, and also Seaborn. I'm not going to use Plotly Express today. And then we will be loading different classification libraries from scikit-learn. So we will use k-neighbors classifier, a decision tree classifier, and also support vector classifier from support vector machines. And then we will use label encoder. This is when you're going to do machine learning, all your variables that you're going to be training your model on must be numeric. So if your data set has categorical variables, like in this case, we have 3 categorical variables, and we are going to convert those categorical variables into numeric variables. And then we're going to, all the numeric variables are going to be normalized. Just a second. Myself. Okay, sorry. Okay, so I was talking, when you're training a model, all your variables must be numeric. And in this case, we have several categorical variables. In the case of the penguins, the categorical variables are the species, the island where they live, and also the gender, which is male and female. So we need to convert all those categorical variables into numeric, and we will be using the label encoder. And then all the numerical variables are going to be normalized, meaning that we will apply a transformation to convert all the numerical variables into a normal distribution, Gaussian distribution with mean equals 0 and standard deviation equals 1. So we are normalizing the data. So we don't have data that is very high, has very large values and variables that have very low, small values. So we're going to normalize them. We're going to use the train test split function to split our data. And this is the standard scalar. That's the one that converts into a standard normalized probability distribution. And then we will use several metrics like the confusion matrix, the accuracy score, the ROC curve, and some other ones. We will see them in a while. All right, so let's start. Okay, so we're going to read this file name that I have in GitHub, which is the penguins data set. I'm going to be using pandas, the read CSV function, to read that file that is on GitHub. And I'm going to define a data frame, which is called dfdist, or distribution data frame. So I'm going to, let me run first, load all the libraries. Yes, run. And it's loading all the libraries to the memory or working memory. And when it's done, then I can read the data set from GitHub using pandas, using the function read CSV. Okay. So, okay. Still running. So wait until we have the green check mark. Okay, so it's done. And then we're going to read the data set. And this is the first lines of the data set. So these are the variables, species. We have 3 types of species for the penguins. We have islands. We have 3 islands also. And then we have physical characteristics of each species. So we have culmen length for every penguin, the culmen depth, which is the peak, and also the flipper length, body mass, and also, we have the gender, which is male or female. And we have some missing numbers, not a number, NaN. So we have some empty values. We will have to use pandas to pre-process our data to make it clean. By the way, Google Colab offers you some recommended plots and also generate code to analyze your data set. But I'm going to go ahead and not accept that offer. Okay, so we're going to do some data cleaning and manipulations using the pandas library. So first, we can use the function info to see what is the distribution, the original distribution of the data frame. And we have 344 rows. And remember, Python counts from 0. So we have rows from 0 to 343. And then we have 7 columns: the species, the island, the culmen length, the culmen depth, the flipper length, body mass, and gender, sex. And we have a different number of values. We have some rows that are complete and some rows that are missing some values. So we have from 344 to 334. So we have some missing values. Okay, so we have to, we can use the function isNull to tell me all the rows, how many rows are empty. So we have some missing values in culmen length, the culmen depth, the flipper length, body mass, and sex. So we can drop all the rows that have empty values using the function drop NA. So I'm going to drop, and then I inquire again what's the status of my data set. And this data set now has 334. So every column has 334 rows. And then we're going to encode the categorical variables, as I was mentioning, using the function label encoder. So we have 3 categorical variables: species, island, and sex. And then we can use the function value counts to count how many different values we have of species, how many different values we have from island, and how many values we have for gender. So I execute this cell, and then we have 146 species from Adelie, 120 from Gentoo, and 68 from Shinstrap. And we have, from the different islands, we have 164 penguins from Biscoe, 123 from Dream, and 47 from the Torgensen Island. And gender, we have 168 males, 165 females, and there is a row that has a dot in the gender. So we need to eliminate this. if we don't have any more information. So I need to apply a filter to eliminate the rows from the column sex. So I'm going to keep only the rows which are different than dot. And then this will be my new data frame, df. And so I will execute it. And now I have 168 males, 165 females, and nothing else. Okay, so now we can do the info function to see what is the status of my data set or data frame. And we have 333 rows for each column. So now we have a clean data set. And we have used pandas to pre-process and clean and our data set and have a clean data frame so we can start. All right. The next step is to encode all the categorical variables. So I'm going to transform species, island, and sex and declare a new variable called species encoded, island encoded, and sex encoded. So I do that. And now I print the first 5 lines of my data frame. So these are the variables: species, island, culmen length, culmen depth, flipper length, body mass, sex, and then the species encoded. So for the species encoded, since I have 3 species, the values will be 0, 1, or 2. We have 3 islands. The values will be 0, 1, or 2, and we have 2 genders, 0 or 1. Okay. Okay, now I have a numeric data frame. Now it would be good to check if we have any outlier values. Can someone tell me what's an outlier? Are you familiar with that? Yes, no? Yes, those are extreme values that yes, that they are completely off. So sometimes these outliers may be just some error, or probably it has a meaning, but then you have to find out what is the reason that you have all these outliers. Okay, so Tuki proposed a method for identifying outliers, and an outlier, by its definition, is you have all your distributed data, and you separate your data by quartiles, and then this will be the first quartile, which is 25% of your data, and this is another quartile. So you have here half of your data lie in this part, and then another 25% of your data rely here. So let's say okay. So and then they defined these fences. So this will be an inner fence, and then this is like 1.5, the interquartile range. So this is the first quartile, Q1 minus 1.5 interquartile difference is going to be this boundary. And then you can define an external fence going Q1 minus 3 times the interquartile range. So, okay, so that's the way you define it. This is the code for defining all the different fences. And you have the inner fence. The inner fence is just the Q1 minus 1.5 interquartile range, or above the third quartile plus the plus 1.5 the interquartile range, and the same thing 3 times that interquartile range. So we see if we have any values First, we define the fences, and then we read the file and see and classify if we have outliers there. There are no outliers in the Coulomb length. We check on the Coulomb depth. Also, we don't find any outliers. And then on the flipper length, we don't find any outliers. And also on the body mass, also there isn't any outlier. So we are fine. And then we can use Matplotlib, PyPlot, and Seaborn to see how your data is distributed. So we have this data frame. So this is the data frame we're doing. And then we can use Seaborn histplot to create some histograms for the Coulomb length and Coulomb depth. I'm defining 25 bins, and also I'm going to plot the kernel density estimate. And I'm going to make two plots in the same row. So I'm using the function subplots. And these are the axis for the first plot and the axis for the second plot. I will have a figure size of 12 units on the horizontal and 8 units on the vertical. And I'm going to have two columns in the plots in a single row. So you will find this is the result. And make it smaller. Okay. I do the same thing for the flipper length and the body mass. This is the distribution of the values. And then I can use, I can take the advantage of the species and separate the data by species and do the same. So now I have a distribution for each species of penguin for the Coulomb length, the Coulomb depth, the same as the flipper length and the body mass. So I'm just using Seaborn histplot. And then I can do bar plots, Seaborn bar plots to see how is the distribution of the Coulomb length for just specific species. And these are the bar plots for the Coulomb length for the 3 species, the same thing as the Coulomb depth. And I do the same for the flipper length and the body mass. So everything looks okay. I mean, that's the way the data is distributed. So now I can do, I'm going to go and train a model. I'm going to train a model to detect or to classify my data sets based on numerical variables. And I'm going to train it to identify any new data row that doesn't have the gender. So I'm going to create a model that classifies the penguins by gender. So just knowing what is the Coulomb length, the Coulomb depth, the flipper length, the body mass, and the species, I can determine if that new row, the penguin has gender male or female. So that's the model we're going to create. So we're going to only handle the features, the variables, Coulomb length, Coulomb depth, flipper length, body mass, island, and the species. And I'm going to create a model that predicts what's the gender. Okay, so I'm going to create a new data frame with these features, and I'm going to call it X. And the other variable will be the gender, the sex encoded. It's going to be Y. And this is called the target variable. So I'm having the variables or the values for the features. I can try to predict what's the sex. So I'm going to split my data 80% for the training and 20% for the testing. So I define the test size, 20%. Then for reproducibility purposes, I'm going to define my random state to 42. So if you want to get the same results over and over again, you have to specify what is your random seed for your random or pseudo random generator. Okay, so I do that, and I have for the training data, I have 266 rows and 6 columns. For the testing, I have 67 rows and 6 columns, and the white train, I have 266 rows for the gender, and for the testing, I have 67. Okay, this is how it looks, white train. So I have the species number and the sex encoded. And then I'm going to use the standard scalar function to get like a normal distribution that has average 0 and standard deviation 1. So it's the red one. Okay. So I apply it for the X train. So I will have the scaled X train and the scaled X test. And then these are the X train and X test. And this is the transformed variables, which are values for this Gaussian distribution of average 0 and standard deviation 1. So it's just in order to avoid having large numbers, you can see the body mass is in the thousands, and the flipper length and the Coulomb depth are in the tens, and these are in the hundreds. So I do a transformation to have everything normalized between -4 and 4, let's say, or -3 and 3. Okay. Okay, so I have transformed my variables. Now I can do, there's something in the chat. What does KD equals true do here? It just plots the kernel density estimate. If you put it false, it won't draw it. It won't show it. And why do we use transform on test and fit transform or train? We transform all the numerical variables for the training and testing. So all the values will be between -3 and 3, let's say, okay? So that's why we transform everything. So now the training test in the new scale variables are going to be this. And then I'm going to use 3 models for classifiers. I'm going to use the K nearest neighbor classifier. I'm going to use the decision tree classifier and the support vector classifier, SVC. They all are part of the scikit-learn classifier models, and there are more models. So I'm just going to use 3 models to prove how these things work. Okay. So now I'm going to create a model 1, using K nearest neighbor classifier, and I'm going to use 3 neighbors. So I'm going to create this model 1, and then once I create the model 1, I'm going to fit the model 1 using the training scaled and the white train. The white train is just the target, so this is just the gender 0 or 1. I don't need to scale it. And then predict, once I have the model 1 fitted, then I can use the model 1 to predict what would be the outcome of the testing scaled, and this will be my Y prediction. So I'm using my model to predict based on the testing values, and this will be my predicted value. Now, this predicted value can be different than your real value. So I will later use the metrics to see what is my error. Okay. And then I'm going to use to create this report value. So I'm going to see what is my testing value for Y, and then compare it with my prediction. And I'm going to print a report. The same thing, I'm creating a second model, model 2, using the decision tree classifier. And I'm going to define a maximum depth of tree. So if you have a tree, then you just go 3 levels down. And this new model 2, I'm going to feed it using the training scales and the Y train. And then I'm going to predict how well my model 2 works by inputting the testing data. And I will have a predicted value of Y or a gender. And then I'm going to report about this difference between these two. The same thing for the third model using the support vector classifier. I'm going to use a linear kernel and probability true. So you can read about this function over scikit-learn, and it will tell you all the different variables that you can play with. Okay. So start simple, and then you start adding things, and see what is your result. So you can fine tune your model by changing the values of your parameters. For every model, every algorithm has a way of moving some parameters. Okay. All right. So now these are my actual and predicted values. So this is my actual value was 0 and the predicted value was 0. So it seems here there is a difference. My actual value was 0, like male, and the predicted value was the opposite gender. Okay. And the same thing happens along the different rows. So I need to evaluate my model. So I need to also bring new variables or new ways of measuring the errors. And one basic function that we will be using is the confusion matrix. I don't know if you are familiar, but the confusion matrix is just a comparison between the predicted condition and the actual condition. And so this is the matrix. Your total population is the number of positives plus the number of negatives. So this is your matrix. So if something is positive and your model it identified as positive, then you have a true positive. But if your row was positive, but the model predicted as negative, then you have a false negative. And then if something is negative and detects as negative, you have a true negative. And if it was negative, but you detected as positive, then you have false positive. So this is used very widely in doing any clinical tests, right? So you have true positives, true negatives. These are the real values. And when you misinterpret, then you have a false negative. If you identify something negative, but it's positive, it's called false negative, and vice versa. If you have something negative and it's identified as positive, you have false positive. In base of these quantities, TP, true positive, false negative, false positive, and true negatives, they define a set of different metrics. Okay, so you can see, for example, let me just show here. There is a, oh, okay, so nothing here, sorry. Okay, maybe later. All right, so I'm going to use the confusion matrix and comparing the testing versus the prediction for each of the models, for model 1, 2, and 3. And I get these numbers back, okay? But these are not very good for interpreting. So I'm going to use Seaborn And Seaborn has a heat map function, so I can represent this boring set of numbers into more interesting ones. So this is my confusion matrix for the k nearest neighbors, and these are the actual values, and these are on the top are the predicted values, right? So this is positive. So of all the, I have 37 rows for the testing set. I identified 32 positive, and 5 positives were identified as negatives, and identified 28 negatives which were negatives, but there were 2 false positives. So out of the 30 negative values or rows, I only identified 28 as negative, and I missed on 2. So these are the misclassifications. These 5 were classified as negative and were actually positive, and these 2 were positive and they were actually identified as negatives. And the second confusion matrix is something similar. 31 were identified as positive and they were positive, but 6 positives were identified as negatives, and 25 of the negatives were identified as negatives, and 5 of the negatives were misclassified as positives. The same thing for the third model, okay, 33, 4, 3, and 27. Okay, so how do you decide which is a better model from the tree? To identify that, then we have to go and take advantage of these following metrics. So there is this function called classification report function. It will give you a set of metrics, and in base of that, then you can decide what are the different values of the different metrics. So precision and recall, I don't know if you are familiar, but it will just show you. Let's see if I am now. What? Sorry. Okay. Okay, now I have it. Right, so this is precision and recall. The precision is just the true positives divided by the sum of the true positives plus false negatives. The recall is the true positives divided by all the true positive plus the false negatives. Okay, and these are the formulas. And let's see if I have down here. Yes. So down here you will find all the different definitions for different variables. So every group of researchers have their favorite metrics, or depending on what is the application, maybe they have to talk about positive prediction or precision, or can talk about fallout, specificity, true negative rates. And so there are many. You have the F1 score, you have the Jacquard index. So you will find that different groups use different definitions to measure the accuracy of their confusion matrix. All right, so let me go back. And then there's the F1 score and the accuracy. So if you're using scikit-learn, then we can use the different variables. So this function, the classification report, gives you back, for example, when you're using the k nearest neighbors algorithm, you have for these 0 and 1 values, you have precision 0.94 on the positive values and 0.85 precision on the negative values. The recall is 0.86 and 0.93 respectively. The F1 score is 0.90 and 0.89. And the support, the number of positive values were 37, or I think male gender and 30 females. Okay, so the sum of the population is 67. The accuracy is 0.90, and then you can take an average, a macro average of each variable, and the weighted average of each variable. This is for the k nearest neighbors, and this is for the decision tree, all the precision, recall, F1 score, support. You can compute other metrics using scikit-learn. And okay, so this set of numbers is very difficult to interpret. So now what we can do is take advantage of the ROC curve. The ROC curve, which is the receiver operating characteristic curves, and it shows the performance of binary classifiers. In our case, our model is a binary classifier, so it tells me if an item or a species is male or female. So this is my binary classifier. And also, besides binary classifiers, you have multi-label classifiers. Let's say you don't want to predict the gender, male or female, but you want to predict the species. Now you have 3 species, and then your confusion matrix is not going to be 2 by 2 matrix, it's going to be 3 by 3 matrix. So and you can have a multi-label problem, classification problem. Okay, so this is the RC plot, and it will show the area under the curve. So let me do it for the k nearest neighbors classifier. So I have the model, I have the prediction, and then I'm going to use the ROC curve function. I give the training data, the training predicted, and I have some other parameters. Okay, and then I draw it. So here, let me make it smaller. So this is my ROC curve, and it gives you back the area under the curve. So the dotted line is when your model is completely random. It's just classifying random female or male. It doesn't have any precision. It's just a random returning value. But when your model is good, it will start giving more true values compared with the false positive. So this is my curve. True positive rate versus true false positive rate, and the true positive rate is the number of true positives divided by the number of positive values, and the false positive is the number of false positive divided by the number of true negatives. Okay, so this is the curve, and if your model were 100% precise, always detecting the males as males and the females as females, then this curve will have an area of equals 1. But if the area under the curve is 0.5, that means your model is just random. It's not giving you any answer. It's just answering random. So that's the curve for the k nearest neighbors. The ROC curve for the decision tree classifier is similar, but the area under the curve is 0.93 compared to 0.94. And the third model, which is the support vector machine classifier, the area under the curve is 0.91. So what model would you select? You select the model which has the highest ROC curve on area. So in our case, we have 0.94, 0.93, and 0.91. So our best model from the 3 that we have used was the k nearest neighbor classifier. Okay, you have a question? Okay, and then k nearest neighbor, yes. There is a classifier. There is also a k nearest neighbor regressor. Okay. All right. So in short, this is how you classify, and you have all these different models, classifier models from scikit-learn, and this is how you use the different metrics to predict or to test or to evaluate your models, and you pick the model which has the best area under the curve, and in our case, it was the first model. Okay, so this is what I have. And then you have more information here. You have all the definition of the different metrics, the precision recall, the precision, the recall, true positives divided by true positive plus false positive, which is the number of positives, and accuracy, F1 score. And you can try different metrics. And this there's a large collection of classification metrics that come in scikit-learn. So it's just a matter of you deciding what metric tells you more information, or what are the metrics that are used in your research group or field. And you can find more. Well, I'm not going to use anything from R today. And then you can find more references to learn about classification and regression. What is classification? What are some classification methods? And how to explain the ROC curve and the score. One hot encoded increase accuracy. You have to try. You have to try. One hot encoding, it only gives you 0 and 1s. In our case, we had island and gender, which had 3 values. But I may be mistaken. You have to try. Okay. Yes, and I think one hot encoding gives you categorical variables again. All right. Any more questions? Okay. Well, that's all I have. Next week, let's go back. Next week, we have dimensionality reduction. Again, we will start the unsupervised learning. That means that we don't have to, we just leave the algorithm to do what they are planned to do. So dimensionality reduction is when we have a problem. Like in this case, we have the penguins data set. We have 6 variables. We have the Coulomb depth, the Coulomb length, the flipper length, the body mass, and also the species and the gender. And are those 6 variables all relevant, or maybe there are some other variables which are most relevant than others? Like, for example, probably island doesn't have anything to do because the penguins move freely between islands, right? So something like that. If I'm analyzing a set of data and I have a number of variables, do I really need to handle all the variables simultaneously, or can I simplify my problem? And in order to simplify my problem, for example, in the penguins data set, I have a problem in 6 dimensions. Can I work with a similar problem, a simpler model with only 2 dimensions, for example? And what would those 2 dimensions be? So I need to do some transformation of vector spaces into a simpler vector spaces using linear algebra transformation of variables. Okay, something that you may already know. All right. So if there are any more questions, thank you for connecting, and we have the next workshop coming in 7 minutes, the foundations of open science from by Michele. Okay. Thank you guys. So I'll see you next week.